Okay, we'll get started. Um, so the goal for today is to cover dimensionality reduction, and before we do that, we left somewhere in between with respect to our previous discussion. So we'll finish that quickly first. Also readjust this alignment. Okay. So where we left off last time was being able to discuss t-test. Any questions about t-test in general? Any questions about testing for difference of means? Anything that's not clear? We left off with an exercise, so we'll try to do that exercise in class today. And I think you don't have your computers, but we'll do it on here. And I just wanted to you to get a feeling about what does the testing involve, how do you do this in R. Okay? So we left off here. I have few corrections to make actually. So I said this data is for India. That was not correct. India is only one of the data points on this plot. I had forgotten how I made this plot, so apologies for that. But this plot is actually showing mean BMI distribution across countries. So this is taken from different countries. What I'm actually plotting is the BMI of rural population. So in fact, remove the urban population, and all you are seeing here is what does the BMI distribution look like, the mean BMI distribution across countries, right? So it's kind of not the rawest data that you will have, but given you have what 204 plus countries or 196 plus countries, you will have an idea about if the question is whether the women BMI is different from the men BMI. This is still a valid data set to work with, and that's what the question that we had asked. Otherwise, what kind of data would you need? You would need this data where you have the BMI measurements for the sample, and that sample will involve multiple individuals. So that will be the raw form of the data coming across different countries. What this experiment entails is it did the BMI, it did the mean BMI for each country, and I'm plotting just that. And despite that, we saw there is some bimodality here, right? There are two modes of this distribution. You see a bump here, and then you see a bump here. And it's kind of also there in women. It's not as pronounced. So the question that we were trying to then ask is can what can likely explain the bimodality? We already tested for the null hypothesis. And the way we did this is we first validated whether the distribution followed is approximately normal. If this value is approximately normal, which means that if you plot the theoretical quantiles and the sample quantiles and the lines lie along this line, then you can assume that this is approximately normal. It doesn't actually work as nicely for some population, but even with this caveat, as long as it's not extremely way off, and probably you'll see this example in the assignment where things can be very, very way off, it should be okay to it should be okay to apply a t-test in this case. We applied t-test in R, and we found we did Welch t-test. What is the Welch t-test? How is it different from students t-test? What is the difference between Welch and students? Okay. So you can assume to be, yeah, that's right. So you can assume the variances to be semi-equal in the case of when you apply a student t-test. If the variances are not going to be pooled, they're not going to be equal. Welch is what you would apply, and this is the conservative way, right? You have no assumption about the variances. Okay, what explains the bimodality? Now that I've updated what I was plotted, and apologies again for giving you false information last time. I had forgotten how I plotted this. Okay. But this is the distribution across the mean BMI for a country, and all you're looking into are different data points taken from across different countries. What does it explain? Okay. Okay. Very, very close. So yes, so that is one hypothesis, right? Which is the bump could explain the developmental index of that country. So I posted a plot on Piazza. Anyone had a chance to go through that plot? And any guesses what that y-axis, what's the x-axis of that plot representing? People don't check Piazza. There are 11 of you who have not even activated Piazza, so that's fine. Okay, so we'll now let's just look at, we are going to do this problem, but let's very quickly look at what that data entailed. So I'm going to pull out the example. Okay, I'm going to remove this for now. So this is a very, very easy exercise to do, right? Every day, all this data set is public. So I'm going to just start loading that data set. This data set is hosted here. It's the same URL, except that when I started doing this exercise last time, I had forgotten how I had gotten this, which is sort of very counterintuitive, but it happens sometimes. So this is the men rural. I'm just pulling out the rural BMI for men in 2017, and then I'm doing the same thing with women. I'm putting it together. I'm just plotting it, and this is the plot that you have seen for a while now. The next thing that I did is I just did a Welch t-test. So I simple, very, very simple t-dot test, population 1 or sample 1 versus sample 2. And you get your t statistics, which is minus 2.6. Your degrees of freedom is 388.7. This is defined. This is not integer because the formula for Welch t-test uses standard errors in the calculation of the degrees of freedom. That formula is there on your slide. You don't need to memorize anything for this class. If required, I'll give you. But this is how where that DF comes from, right? And the p-value is 0.007. So we can reject the null hypothesis, which is that the men and the women BMI is equal. Okay, then somebody raised this question about bimodality, and then we started discussing about, is there an echo happening? Yes or no? Okay. Electrical engineers, why is echo happening? Where is that positive feedback? Hmm. Will this help? Will moving it? Why? Okay, think. We'll discuss at the end of the class. Yes, yes, please. QQ test is to test for the data being approximately normal. So when you discuss, if you remember the numerator of the t-score, that difference should approximately be normally distributed. Like that's a very, very loose assumption that we have. The way we are testing this is we are running tests for normality on both the two samples, and if they look approximately normal, the difference will also look approximately normal. So it's not a requirement, it's not a necessity that they should be normal, but if it is normal, the properties are nicer. We get, the assumption about applying can directly hold. If they're not normal, it gets slightly technical, but you lose power basically. That's what happens essentially. So even if there is difference, you'll not be able to detect it if they don't, if they fail the normality test. Is that fair? Okay. So we started looking for the reasons that this could be explained, and there was certain hypotheses about the diet. There was certain hypotheses about the income index, and we have some economics people in the audience, so they are more suited to answer this question than me. But I'll use the approach where I have no knowledge about any economics, but I know, for example, to be able to handle data. So what I did is I went to the World Data Bank, World Bank's data. So WDI is a package which has all the WHO the World Development Index stored. So this makes this it's a package which allows you to store, not store, but search any index that the World Development Bank puts out there, and you can query that, right? So one of the, if your hypothesis is it has to do with the income status of the country, or it has to do with some socio-economic factors, we should be able to bring it in our data and then try to search it. And that's what I did. So first thing I was interested whether are there indexes for GDP per capita, and there are multiple indexes that are stored. There is GDP per capita, PPP, which is purchasing power parity adjustment. We'll not discuss this in this class, but it basically allows you to compare one nation's income or one nation's currency with other currency, adjusting for inflation and other factors, particularly purchasing power. Okay. But for this class, you can assume that you have access to a number which quantifies on an average what is the GDP for each of these countries, having adjusted for other factors that can ideally go wrong, right? So that's what we did for, we can search for that index, and then there are multiple such indexes like that. I can take the purchasing power parity for 2017. So this is what it tells me. Single command, I have the countries, I have the GDPs for each country here, right? So this is what the data looks like. You have, they are sorted in alphabetical order. So you have countries, all the countries data. I think it's 266. It includes territories and those things as well. So that's what is the explanation factor. Then I'm going to just, in this, for the sake of clarity, I'm going to just read the BMI data once more. And I'm going to do what's called a left join. So I have the data for different countries. This is your BMI data. So you can look at what this data looks like. This is just different countries, national, rural, urban, year, BMI, and country, right? And then I also have, in the other data frame, I have the country and its corresponding ISO category, which year is this GDP from, and its corresponding GDP, which is in this column. I'm doing a left join. What this left join allows me to do is it allows me to put these two data frames all together based on one column, which is common, in this case, that being country. So if I do this, it says I'm going to join these two data frames by country. The reason I'm going to do this is because I want to be able to see what is the impact of the GDP on BMI. Is that clear? That's what this particular command does. Very, very simple to understand. It does what it says. Left data frame being joined by the right data frame on a based on a column, which is country, which is common. Okay, then I'm going to cheat a bit and I'm going to just plot everything, right? This is cheating because there is men, there's women, there's national, there's rural, there's urban, but it's fine. I just want to see the trend. So if I plot the, and this is the plot that I posted on Piazza, where I, hid the x-axis, or I try to hide it. This is your GDP adjusted for purchasing power parity. This is your BMI, right? And the hypothesis that some people had in the class is true. Okay, now if that is true, right, we can do somewhat better of a job, because this is cheating, because there's everything there. There's women, there's men, and there is all sorts of national, rural, urban thing. Let's make the data very, very clear. So just subset to men, rural 2017 population. I'm going to do one adjustment. So in the uh, BMI index data frame, the country is called United States of America. One of the countries obviously is United States of America. In the GDP data, that same country is called United States. Just for the sake of clarity, I'm going to rename United States of America to United States. I'm going to do the same thing again, and now I'll plot this data. I also decided to highlight some countries based on what I thought would be interesting to see. So what you see here is United States is all the way up here. This is again GDP adjusted for all things that you would want to adjust it for. This is China, this is India, and this is Somalia, Zimbabwe, Zambia. Right? So what conclusions do you draw from this plot? This is men. This is just men. Yeah. So you do see bimodality. You have to look for it. Yes. Hmm. Good question. Yeah, good. Oceania. So these are all coming from Oceania, which is neighboring in the South Pacific Ocean. So yes, that's a good hypothesis. That's one thing. A lot of islands there which have very high BMI. So biomodality comes from your BMI, right? So biomodality comes in this fashion. You, so you have more number points here, right? So if you want to, so just so that we all understand where is the bimodality coming from. So this bimodality still remains, right? The bimodality is coming because there are certain countries which have very low BMI, and if you go and look at in this plot, so for example, these set of points that you're seeing here, that is the lower uh, BMI. This pool of countries has higher BMI. So when you plot them just with respect to BMI, that appears as two modes. So there is difference in terms of the men data is more bimodal as compared to women data, but there is bimodality in both the scenarios, right? So for example, if you look at this plot, the women follow a slightly lesser mode as compared to the other one. That what I'm looking at, I'm forcing you to think about only the men data because that's much clearer in terms of its bimodality, right? So that was what the focus was. Is that clear? So very easy to check things once you have some hold of what question that you're trying to ask. Any other questions about this data before we move on to other things? Yeah, so good question. You should test this, right? So I'll give you the code. Test whether what is. I did not check for each and every country which lies in that population. If you want to do this in a comprehensive fashion, you will take that smaller pool and you will just check the frequency of which continent is represented there more. You could do that. I have not done that, but from a very brief check, it does appear as if the the poorer countries obviously have poorer BMI, and if you know the poorer countries, it's easy to predict what the BMI would be. Okay. Any other questions? Okay, so then we started to do this simple exercise, right, where we were testing for vitamin C and placebo. Um, this data is very simple, but I wanted to use this as an exercise to teach you about how to visualize it, right? So all this class we've been talking about statistics, and we have done some visualization, but we have not done any proper visualization about, okay, if I'm giving this kind of two sample population or observations from two sample population, how should I visualize it? How would you visualize this kind of data? I want to see, right? I know my null hypothesis. So my null hypothesis in this case is vitamin C has no difference in the length of stay as compared to placebo, or the length of stay for vitamin C treated and placebo treated students or children or patients is same. How do I visualize this data that is presented here? This all of you should be able to answer. Yes. Okay, bar graph with standard error. So what is a bar graph with standard error? So this will be vitamin C and this will be placebo. Why bar graph? Good question. Yes, please help me with the correct. Okay. Because its mean is bigger, right? 7.125. Okay. So this is 6.5, 6.45. Yeah, so 6.5, 7.125. If I showed you just this, would you be able to conclude that placebo is higher? It's different if the difference in the length of stay is higher from placebo as compared to vitamin C, just based on this plot. Can you say that? You cannot say that, right? Why you cannot say that? But let's assume that that's the only data that you have. We can't do better. Sorry, you tell me. Is there a way to use students T? Okay. Okay. So we can use a Welch test, right? So hopefully does that answer your question? We can use Welch test. My question is slightly different. So we'll come to the statistics. We'll do the statistics in just a bit. I'm asking if somebody put this figure, you use slides, right? So if you're going to labs, you must be doing some sort of visualization. If somebody showed you this kind of slide, what would you conclude from this? Can you conclude anything from this? No. Yeah. So one thing always remember, right? Whatever is given to you, right? This is the sample mean. This is the sample mean, right? So this is mu1, this is mu2. Gautam said to plot the mean, right? So this bar plot represents the height, represents the mean of these population, right? So this is this is mu1, mu2. The reason you cannot conclude anything from this is you have no idea about how much variation in the mean you have, right? So if you start from a very small sample, this represents your standard error of the mean. Everyone now understands what the standard error of the mean is? Anyone who doesn't understand what's the standard error of the mean? So when we take a sample, if this is our sample, this is our population. Sorry? Standard deviation of the mean, exactly, right? So this is standard deviation of the mean, which is what it's slightly more technical than that, but it's sigma by root n, which is your population mean divided by, or your population variance divided by square root of n, which you don't have access to, so you use the standard deviation. Yes. Why are we not using what? Population adjustment factor of. Mhm. So, okay, I see. So in that case, yes, so you can assume that correction to be very small. So that's the right way to do it, but you can assume that correction to be very small. So we'll come to that question in just a bit. Let's just understand it. If I have to visualize this, why can I just not conclude from this data? Yes. Yes. Yes, we are in the regime of comparing the means, right? So if you wanted to compare given certain categories, has the distribution changed, you will use chi-square test, right? This could involve if you're testing across months. This could involve if you're testing across a certain blood type population. So for example, one test that you could think of is the where you would apply chi-square test is all of you have blood groups, right? So A, B, O positive. These are like distinct categories. If I count the number of people who have A, B, and O here, and I go to the other class and try to test it, there the chi-square test is more applicable, right? Because of what I'm testing is the relative frequency of a particular category, has it changed or not? Is in the t-test, what I'm testing for is the mean difference between the populations different. So I cannot obviously test this if I'm counting the blood group. But if I'm counting, for example, their hemoglobin levels, then I can apply t-test. Does that make sense? The t is the student's t. So it's the distribution that you're assuming for, right? So what is t in the t-test, right? So the t-test comes from the same distribution that we saw, which is student's t. So if you, this is your t, right? And this is your Z. So it has fatter tails, basically. If you remember that diagram, that has fatter tail. T has fatter tails. What follows a T, right? So if you're, it's a distribution, it's a number which would have some kind of this format, okay, where this is approximately normal and standard error is independent of your uh, x minus mu. The reason we are applying this is because we don't know the population variance. Had we known the population variance, this would collapse to becoming a standard normal, right? You could always collapse anything which is divided by standard by a normal divided by the any quantity to look like a standard normal. But we don't know this. That's where the fatter tails help. Does that make sense? So the denominator is a quantity which is just the standard error of your numerator quantity that you are measuring. Okay, so this is y1. So these are two populations. So this is y1 bar minus y2 bar. I'm testing for difference of means. And in the denominator, I'm dividing it by what is the standard error of the difference of the means. It's not a constant. It's a random variable. Yeah, it's a random variable. It's a random variable, right? So these are both random variables. Okay. Does that make sense? Anyone else has this confusion about T, Z, why T, why are we doing this? Mm-hmm. So that convention is, I think that convention is for, it's not, it's not wrong, but it's also not correct. The reason that convention works is because if you have enough number of sample sizes, you can assume that things, because of, huh? Exactly. So you'll start to assume that, but ideally, in you work, if you want more power, so the reason you would not want to use z-test is you'll miss out on things which are more important, right? So this is the regime that again comes to the idea of power, which we very briefly discussed, like what is power, right? Which is being able to detect differences if they're actually there. Now, all the reason that you're doing and trying to go forward to think about what is this really distribution is to be able to capture everything. The more you are able to sort of capture this properly, more is your ability to be able to detect these differences. Otherwise, I would not have been even up to apply these tests. I would have just been able to do what's called a Mann-Whitney U test, which is non-parametric, where I just look at the rank differences between these two observations and be able to draw conclusions from there. But the reason we don't want to do that by default is because if we can do a better job, right? If we can figure out that whether these assumptions hold, then we can apply a slightly more powerful test, right? So that's what we did by when we check for normality. That's what the reason was, that we check, okay, the differences are approximately normal. We don't know the population variances, but t-test is the most powerful test in this case. Okay. Any other questions? Any other questions? So how does this come out to be? T is slightly technical, but if you go and read the PDF of this, which follows a gamma, again the mother distribution, you will see that there is some relationship between what's in the numerator and what's in the denominator, right? So that's where this collapses to a T. Otherwise, you could have just worked with a Z test. I don't need to explicitly do a T test, right? I could have just treated this as a normal variable and just applied the z-test and I would have been fine. But we are trying to do a slightly better job because we don't know the standard, we don't know the population variance, and hence we don't know what the standard error of the mean difference would be. Is that clear? Any other questions? Okay, so back to this original question. So you must have all plotted some sort of a bar plot, right? When is a bar plot used? So bar plot is something that you would want to use if you want to show frequencies, right? That's what the definition, that's where the bar plot actually arose from. in this case, right? So in this case, you can also use bar plots to show the means. So this could be mean, which is not a frequency, it's a continuous number. But if I just show 6.45 and 7.125, I cannot by just looking at this conclude that this is different. The only possibility, the only reason I would be able to conclude this is I will take the difference, right? So let's do that example which came up in the class, right? So 7.125 minus 6.45. Can somebody help me with this? Otherwise, I'll help myself. So is this correct? Is this correct? This is correct? Should be correct, right? It's correct, right? No? Where did I go wrong? Oh, yes, sorry, that's right. Okay, 0.45 plus the 0.125, yes, 0.55 plus 0.125, right? So, okay, so if I look at 0.675, right, this is the difference that you have. Now, think about the standard normal again, right? So this is 0. You're seeing this area, right? You're seeing this area to be, so if I assume this to be, if I'll have to divide this by something, some sigma to make it a standard normal. Let's say that sigma I will use, let's say I will do some cheating. So I will use it, it's 0.24 and 0.254, right? So let me just divide it by, okay, 0.24. How much does this come to be? How much? 2.8, yeah, approximately 3. Okay, now where will 2.8 belong on this curve? So I told you, if you want to cheat a bit again, this curve practically for all practical reasons ends at 3, right? So 2.8 will be somewhere here, which means it's going to be what? Is it going to be significant or not? Approximately significant, right? I would say approximately significant. It's very, very close to towards the boundary of the z-score, right? So we would have been able to do this, you know, this is okay, but we know that this assumption is not correct. And that's where that assumption that we cannot assume, we know that these standard errors are different. We know that the population sizes are different. So we need to be able to account for that fact. And that's where we are doing a t-test. So if you see a plot like this, you cannot draw any conclusion from it. The reason you cannot draw any conclusion from it is because you don't know what is the variation within that particular group itself. You just got maybe lucky and your mean happened, the sample that you drew, your mean happened to be here, right? But if you were to next time repeat the same experiment, maybe your entry comes here and this entry comes here. Okay, and then you lost all the information. So before making any conclusion about this, you need to see what is the variation within that group, and that's what the job of the standard error is. Okay, everyone with me? So anytime you see a bar plot, always ask for where is the standard error, right? In most cases, it's fine. It's going to look, it should ideally look very small, which will tell you that you can actually believe this bar that you're seeing, right? And I wanted to talk about how to sort of visualize this information, okay? So this is what the bar plot, the box plot for, this is okay. So I jumped a bit. So this is your bar plot, yes. Mm-hmm. I approximated it. Yes. We'll go to the formula for the Welch t-test. What it does is it pools this two information, having accounted for the sample size that you have. So that formula is there in the previous slide. If you want, I can bring it up, but it is okay. So you'll see that even I don't remember it, but I'll try my best. Can somebody verify? I think this is Is this correct? I think there's something so this is in the pooled case. There is one more adjustment required, but you can assume with this version. Yeah. There is actually one, -2, which is because it's from 2, but for all practice. So you have to always do this actually. The sample size cutoff that you're talking about is you have to apply for a small size correction, which we'll ignore for this case. Okay. Does that answer your question? Sorry. So this, okay, I'll just call this is SD of that sample. This is standard deviation of that sample squared plus standard deviation of the second sample squared by n1 plus n2 plus n1 minus 2. Okay. Any other confusion about this? N minus 1. Oh, okay. So multiplied by n minus 1. Okay. Okay. And what about the denominator? That remains the same. Okay. So let me look it up. Actually, that's the easiest way because that's intuitively that's the first thing that I wrote. Okay. So in this case, actually, it's even simpler than this. So this all you're doing in all the cases is you're simply dividing it by some variation of the difference of the means divided by your standard error. This standard error, if you are able to pool information, which is you assume that they're of equal size and they follow the same variance, you can divide it simply by the summation of the two or take a weighted mean of these two. Or this is again standard deviation. Okay. Soumyadeep, no, what's Soumyadeep? Right. So the second one is when you assume equal or unequal size variances, but you assume they have similar variances, right? Then you apply n1 minus 1, which is what I wrote actually initially. N1 minus 1 sx square plus n2 minus 1 divided by n1 plus n2 minus 2. And finally, if you have totally sort of forgotten about, you assume totally unequal variances, which is actually the test that we are doing. We do DF, we do the standard error comes from this formula, or the denominator comes from this formula, and your degrees of freedom becomes slightly more complicated. Okay, so we'll not get into technicalities about which approximation is correct. My to-go advice would be to be conservative and use Welch test, which uses least number of assumptions of your data. Okay. Yes. Sorry. SP is the pooled sample in this case. So the SP is whatever that SP is defined. It's defined corresponding to that. So SP is the pooled sample x1 square, x2 square, and x1 square is your simply variance of your sample x1. In this case, you don't know anything about the population, right? So you'll not be able to estimate any population. So you're using the standard deviation squared, which is basically your variance. What's the confusion? What's the confusion? The SP. So you're talking about this SP first, SP? Yeah. So it's basically you're pooling the variances of the two, right? So if you sum, so okay, let me just clarify this. So what is the assumption of equal size and same variance, right? So if x1 and x2 follow the same variance, what is this equal to? If they are independent, what does this equal to? Okay. Okay. Now this is equal to what? Is that fair? So this is SP. Okay. All it is doing, it's writing it in that particular format. Okay. The sample sizes are equal, so that's why that root n is the same there. Make sense? Everyone clear with that formula? Any other doubts? Any other questions? Okay. Okay. Thank you for asking that question. It's always good to reflect. Any other doubts? Summary, right? Question clear? Everything is clear? Yes, question? Okay. So I showed you a plot without actually motivating what's the use for this, right? So you would have been able to draw this and that's totally fine, but it hides a few sets of information. So every information that I'm showing this on this bar plot, it assumes that if I'm showing a bar, then everything came from that distribution. I'm not able to see what is, if I did 10, 15, 20 observations, are all of them distributed in a similar fashion? Are all of them located towards this mean value, or they are very, very different, right? So one way to fix this is to make this, which is a very, very easy fix, is to draw something called a box plot. So this is vitamin C, this is placebo. Okay. So what you're seeing here, and this will become clear in the next plot, is this is your median. This is your median of the data. This is your Q2. This is your Q1 minus your 1.5. This is your Q2 minus your 1.5 IQR, and we'll define what that IQR is in just a bit. Okay. So don't worry about what IQR is for now. What we want to see is we want to be able to visualize where is my median of the data. This quantifies that this is your median is located here. Whereas the whisker shows you what is the upper extreme in terms of how much data you're seeing within certain boundaries, and it will become clear in the next slide what these boundaries are and how do they make sense. Till it becomes clear, try to think why should I draw certain whiskers? What is the quantification of it? We'll see this in just a bit. Okay, so I'll just show you what the box plot looks like. Right, so the box plot looks like um, the figure on the left is an example without outliers, and the figure on the right is a data point where you see something here or something here, which lies beyond your control, right? Which is something which is outside your control. So, sorry, this is Q3 and this is Q1. So what this is telling you is giving you all the modes or all the information about data. So beyond this, any data point that exists, this represents that 25% of your data point lie below this line. This line represents 75% of your data lies from here to all the way down there. And then these whiskers or these sort of stems here represent what 1.5 times IQR that remains here. Okay, and we'll just see this in a bit. What is the why do we use 1.5 IQR? So anything which is beyond these 1.5 IQR, beyond Q1 or Q3 becomes an outlier. Okay. Any guesses on what is the significance of that 1.5 IQR? Why 1.5? Any assumption that we are trying to make when we try to draw this? What is sort of the underlying assumption? Why should looking at Q1, which is everyone understands what's a quartile? So 25, this is the first quartile, which means that 25% of your data lies below this line. This is your third quartile, 75% lies below this line. This is your second, which is your median. So 50% of your data lies below this line. Okay. Why would I want to look at that information and as compared to a bar plot? So this I'm sure, assuming all of you have seen in your life, right? Box plot. What is the significance of 1.5 IQR? Why 1.5? Why not 1? Why not 0.5? How? How? Why would that happen? Okay, very, very good. Okay, very, very good, right? So this is exactly why that 1.5 number makes sense, right? So this is 50% of your data sits between Q1 and Q3. This is by definition. Q1 is below is 25, Q3 below is 75. This is your 50% mass of the data. Something that your information, which is just a bar plot, is going to hide. You don't know what does the distribution look like. You know the summary of it, but you don't really know, is most of my mass here, is it here, is it here, where exactly, right? So that's why this is not usual, not something that you would want to compare if you're comparing for two different means. When you bring the box plot, this is assumption that if assuming things are Gaussian distributed, which is true for most of the cases, you would want to see what amount of information is there, what is the major chunk of information which is there. So this Q1 to Q3 captures 50%. The remaining 24.65% is what is captured in the 1.5 QR, right? So if you add this, you are close to that 3 sigma magic number. Not exactly, you are around close to 2.96, but that's what you try to capture. That most of your amount of your information is being captured in that particular area. Is this clear? Why 1.5 IQR and not just any other number? Any questions? So you've all seen box plot, right? So whenever you're comparing box mean differences, you should use a box plot. Okay. So very quickly, we'll switch over to that example. So in this case, I've just taken the data from the exercise, put this in numbers, and I'm going to just compare them, right? So all I'm doing is I put these numbers together. I define the mean, I define the number of samples, I define the standard deviation, I define the standard error. This is based on my definition, right? This is based on just standard deviation divided by the sigma of root n. That's your standard error. And then I can quantify what is my standard error of the difference, right? So this is what I'm doing here. I'm just taking the sum of the squares, which is what I did, what I showed on the plot here, which is simply the summation of the two variances of the two population or the two samples, right? Okay, so I can do the t statistic on my own, right? So I can divide it based on uh, this number here, t stat. This I'm going to force you to think for now. It's 11. You can calculate this based on the formula that I put that in the slide. All I'm doing here is I'm taking the mean differences between the two samples, dividing it by the standard the standard error of the difference, and just calculating my t statistic, which is 1.925. Okay. If I want to calculate my p value, I can just I can just ask R to give me the probability of observing something as extreme as t statistic. So for this, you'll have to read the documentation of why I decided to choose the way this is defined. That's because this particular function gives you the left area, right? So I am asking what is the area if my t statistic is at least as strong, which is in this direction. But since I did not specify the direction, I'm multiplying this number by 2 to get the right half. Is that clear what I'm doing here? So that's why I'm doing 2 times the p-value. Okay, so I get 0.08. And here, when I actually do the Welch test, I get a slightly different value. The reason for that slightly difference is because I approximated the degrees of freedom to be 11. So that was a lose-lose definition of DF. But here, that degrees of freedom, if you go back and calculate from the Welch formula, is 19.96, right? But overall, in terms of what that has done, the p-value has shrunken from 0.08 to 0.06. The conclusion does not change, right? So this is To do this calculation by hand, very simple, the second version where I can just pool the information of the standard deviation, pool the information about the degrees of freedom, and then do the test versus doing a Welch test, right? So what I'm doing here is Welch test in R by default. If you want to switch this off, there is a variation where I can say that by default it assumes that the variance of those two populations is not equal, excuse me. Right? So if I switch this off now, the p-value and the degrees of freedom again change because you are now applying a slightly different version of the test. Okay, is that clear what is happening? Any questions? Yashwant, is that clear? Questions, concerns? Too much confusion? Okay, so you'll do this as part of your exercise, right? So don't get bogged down by the amount of information here. Once you start to get a flavor, so for this you'll have to get a flavor of being able to do these kind of tests, and then um, this will start to become more and more clear. Okay, but is the broad goal what we are trying to do? Is that clear? We're trying to test the differences of two populations, right? And you can also apply a z test here, right? So for example, I could have, if I wanted, I know the difference. So this is minus 0.675. If I assume this to be a standard normal, which it is not, I could just ask what is my so now I'm asking it to tell me what is the probability of seeing a value which is as extreme as minus 0.675. Okay. So this is 0.249. It's very, very small. I'll multiply this by 2. You're basically, if you're looking at just minus 0.675 difference, you're located somewhere close to 0. Is that intuitive? If I had no idea about the standard error, if I just totally ignored that information, I would have falsely, I mean, in this case, the conclusion does not change, but the test statistic that you're getting, that changes. Okay. So here, if I assumed, so what you are seeing on the, let's just try to visualize what you're seeing, right? So this is your standard Z curve. If I ignored all the standard error information, if I just assume that they are all coming from a standard normal distribution, my test statistic lies here. Okay, this is minus 0.675. So this area is going to be very, very large, right? So that value, that's what the value that you see, which is around 0.25. Okay. Similarly, the p-value, if you calculate, will be 2 times this because I did not specify the direction. However, when I do the t-test, I'm accounting for, I don't know the variance. I cannot assume that they follow the standard normal distribution. So for that, what I do is I start from a different curve which has slightly fatter tail. This is your t, this is your z, and then you come and ask, okay, now if I don't know the standard error, let me calculate it from the data itself and then come back and see where my test statistic lies. Is that clear now? Okay. Any confusion, please stop me. Please tell me right now. So in this case, that's why you have to focus on the null hypothesis, right? The null hypothesis that they're not equal. I could have started from this null hypothesis where my alternate hypothesis was I started from this null hypothesis that they're equal, and my alternate hypothesis being that they're not equal. I don't care about the direction right now. It's two-sided, right? So you can again see what is the alternative. So you can specify it. Let's do it actually, right? So the alternative here is two-sided, less or greater. You can actually specify what the alternative is. By default, it's two-sided. Okay. So let's do the same test where I can now specify my alternative is, so this is population 1, vitamin C is population 1, placebo is your population 2. I can just say that, okay, my population, my alternate hypothesis is that it is greater. Okay, what happens to the p-value? Any reason why it's so high? Why is it so high? Okay, but why? Why is it so high? Right, almost exactly. Right, it's exactly on the opposite side. Right, does that make sense intuitively? So what I began with is this mean. Right, you can see it here. I'm saying that I know that this mean is smaller, but my alternative I'm saying is it's greater. Right, so there is no way that you will be able to accept that particular alternative. Right, makes intuitive sense. Okay, any other questions? Okay, so this was 6.45. This is 7.125, right? My H naught in both the scenarios is the same, which is mu1 is mu2. My H alternative is mu1 is greater than mu2 in this case. Okay. So when I do this test, what is the definition of p-value? Yes, but you have to focus on what you're testing exactly, right? So in one case, what you're asking is, let me just draw it. So this is your test statistic, right? So the test statistic is there is something in the numerator which is a variation of mu1 minus mu2. In most cases, mu1 minus mu2, and then in the denominator it's this thing, right? Now, what is p-value? So my p-value for h naught is mu1 is equal to mu2, and h alternate is mu1 is not equal to mu2, right? So I get some statistic, right? So let's say I get this value here, okay? This is my t statistic value that you get. How will I assign it? What is the p-value? Is I'm going to ask what is the probability of seeing something as extreme, okay? Focus on what you're hypothesizing. The second hypothesis is that it's not equal. So I'm going to say, okay, I will see this side to be as extreme, but I will also see this side to be as extreme because there is no direction that I specified. Okay. Now, if I specify the direction, right? So I got my t statistic to be this number here, right? Some minus whatever, minus t. My alternate is what is the probability of seeing something as extreme as you saw, given this is your alternate option. It becomes a one-tailed problem. That's why it exceeds even 0.5, it's 0.9. Does that make sense? Everyone clear? Any questions? One-tailed versus two-tailed, that's the difference, right? Any questions about that? Okay. So finally, hopefully we'll be able to get back to doing some visualization. Okay, so very quickly I'll show you that if you want to do, this is all statistics, right? But as humans, you want to be also intuitive. That do you see it visually? Like, can you really see it? So I will plot this. This is what that box plot looks like, right? So here you can see what is happening. This is your quantile. This is your median of placebo. It seems to be higher. The question that I'm asking is, okay, I do see it to be higher, but can I make a claim that this is going to be statistically significant? That's where your t-testing or any sort of testing framework comes up. This is just a step that you would want to do before you do anything. Anything else that you would like to change in this visualization? Does it show you all the points? What does it show you? Does it show you that all the data points are here? Like, are all the data points within this boundaries? Or can they be uniformly distributed here? Or are they biased in certain direction? It doesn't show you that, right? Any other thing that you can think of how to fix this visualization? This is not a statistic question. This is a question of design and intuition, right? So hopefully Again, it doesn't require a degree or a course in design. Exactly. You can have a curve which tries to sort of capture it, right? Great. So that's what this curve would help you to do, right? So you could do what's called a violin plot, which shows you the relative distribution of this thing, right? So here I'm hiding the information about the median, right? You can always superimpose it, but this is what's called a violin plot. The reason it's called violin, well, is because it looks like a violin. It has, or partially like a violin. So it has this fat tail here, or sorry, the fat mass here, which tells you that for this particular variable, most of the observations are actually lying here. They're not in the extremes, right? And similarly, for this one, this is slightly taller, so means that even though the means is different, so this is where the means is, the distribution itself is different for different variables. This is a toy data set because the data set that we have doesn't have enough observations um, to show you to motivate this particular reason. But you'll do this example in your assignment, so things will become more clear. So violin plot, if you just do it by default, right, it's very simple. You just give it a geom violin and it plots the violin for you. But it is lacking quantitative information. I don't know where the mean is. I don't know where the quantile one is, and so on. So I can overlay both of them together, and now I have both the information. I know where the quantile is. I know where the median is. I know how many observations are there within that boundary, but I also know the spread of the data. Okay. Any other fixes that you can do with this? Any other visualization that you would want to think of? So this is, by the way, a field in itself where people try to think about different visualization techniques. Any way to fix it? What is lacking? I get the distribution, but I'm very finicky. So I want to really look at what is each of the data points really there, how many data points are there. It is hiding that information, right? It's hiding the information about how many data points are there within each observation. Is it 10? Is it 12? Is it 15? Is it 20? You can always make these kind of curves with even 10 points. I can make this kind of curve with 100 points. How will you add that information here? No, you cannot do that for this violin. Good suggestion, but you cannot do that because you cannot scale them based on the number. Is that what you're saying? The width? Okay. Okay. So the by definition and by design, excuse me, by design, the area that these cover are actually all equal. You're saying that they should be scaled based on the number of observations that you have. Hmm. I think it will lead to awkward plots. Any other fixes? But good thinking. Okay. Any other suggestions? Okay, color. How color? Fair enough. That's a good suggestion. Okay, we can do that. Any other suggestions? Good suggestion. Yes. So we can plot the data points, but if it's 1,000, 5,000, it gets super tricky, right? But there are ways to sort of handle that information. So one way to handle this information, this is just a sort of a brother version of violin plots, is you can plot what's called a ridge line plot. It's very intuitive, right? The moment you see it, you know that this is higher as compared to higher, this is compared to higher, hopefully, right? Statistically also. Here again, you're not able to capture all the point information. So one way to capture this point information is to plot these individual points that you have in your data in the form of the violin, right? So you can think of this as you're doing a histogram, but on the y-axis, such that if you have more observations, this is going to spread wider. So if you get one certain value which is constant across multiple points, you can jitter them. Jittering means that you can add some noise on it so that it starts to spread around, and then it becomes kind of a violin. This is called a bee swarm plot, right? Because you can think of these as bees and they're forming your swarms in terms of being able to sort of visualize what is really happening. This is not very quantitative by itself, You can add a bee swarm along with this violin. So this gives you all the information that you need. You get information about what is the distribution of the individual points, and you can do this, and you can plot the violence over it. You can do this actually very nicely. The reason this works is it actually scales very well, even if you have thousands or more than that number of points, right? So I'll probably share the examples of those plots in the slide when I upload it, but it's a very scalable version, right? So whenever you're thinking about testing for means, you're trying to show this information. This is the most honest plot that you can show anyone. You show the points, you show the quantiles, you show the spread of the data. Okay, you can in fact overlay a box plot also on it. It doesn't tell you the number of points. Yeah, so it tells you the number of points because yeah, so you can try to sort of squeeze through your eyes and try to see whether is it, in this case you cannot see the difference because they're made of similar number of points, but if there is huge difference then that starts to appear up here. Okay. I also reduced the size of the point, so I did not do a good justice. Let's actually replot this. So I can replot this, hopefully. Okay. I reduced the size of the points, so I'm going to reduce it back to 0.5 and let's see if that helps. Okay, is that better? The number of points you can, no, you can help the reader, right? You can help the reader at the top by saying these are the number of points, or you can do a joint plot where you can say that this is what my mean distribution looks like, and at the bottom of it you show the number of points for each of these observations. You could do that, right? So you can think of this is your violin plot, and at the bottom for the same category you're plotting the number of points if you want to be really visually clear. Okay. Okay, then we'll start the fun part of the course, which is the dimensionality reduction. Right. So let me start off with giving you an example of what we are trying to talk about. So this is a survey data taken from the National Family Health Survey. It measures 131 different variables across different states. So the survey people, they go, they have a certain sample set of households that they have already pre-selected based on certain criteria that it represents the entire population. They go and they ask like these 131 different kind of questions. That includes questions about what kind of fuel you're using for cooking, what kind of whether you had a baby or not, like, and what is your blood glucose levels? Are you taking medicines for your blood glucose? Are you taking medicines for your hypertension? So it's like 131 variables, right? So if you want to start to do anything informative about or with this data, it gets tricky because there are too many variables. So how do you figure out what you really want to focus on? But given this India data is across India, the first question that you can ask is there some sort of structure in this data? Is there some sort of information that I can capture from these number of variables, right? So the first question that you would ask, given such high dimensional data, so you can think of this as a high dimensional data. Your rows are your different states, the columns are your different variables, right? So it's a data which is what, 36 cross 131. It's not that big, right? But if I want to do anything meaningful with it, and if I don't have a question in mind, the first question that I will have in mind is, what does it really tell me about India? Okay, is that a fair question to ask? What does it really tell me about India? Okay. So if this is what we want to do, we want to reduce those 131 dimensions to a handable number of dimensions, right? So this is a 131 dimensional matrix, right? How do you visualize this? That's the question that we are trying to ask. Without doing anything very quantitative, if I just want a visual summary of my data, how can I get it? And one way to do this is to use what's called principal component analysis, or PCA. I just realized that I started with a short form without explaining what it is. Have people seen or heard about this term? Is this spelling correct actually? Or is it PLE? It's PL. Right? So it's principal, and we'll see what that principal is in just a bit. Okay, it's not principal. Uh, okay, so imagine you had a very simple problem, right? Very simple problem. You have a data. You have 4 data points in 2 dimension, but I don't want to see 2 dimensions. I don't like to see 2 dimensions. This is just 4 data points. Can I see this? Can you compress this information in 1 dimension? And if yes, how will you do it? That's the question that we will try to ask. We want to be able to do this, right? I'm telling you right now because I don't want to look into 2 dimensions, right? Obviously, this is a very hypothetical and a dumb problem to ask, but I'm saying I don't like to see 2 dimension. I want to see this data in 1 dimension. What are you going to give me? How will you think about it? Okay, so you know this. Okay, finish the argument. Yeah. Okay, so you can project this along which line? So which line should I choose? Best fit line? Should I choose the best fit line? Good question. Okay, very good. Now it will get super interesting. So should we choose a best fit line? So let's assume why best fit line? Minimum deviations from the point. Which point? So with what? How are you defining the deviation here? Okay, this will get very interesting. So okay, fine. Okay, this is what the deviation is. Okay, so is that the deviation that you're minimizing in best fit? Is it correct? Is this the deviation that we minimize in the best fit? People who have done linear regression. Which one is it? This one or this one? Perpendicular? You sure? Hmm? Perpendicular. Okay. So this is so if this is, should I write this as yi dash? What are you trying to minimize then? What is it? Confusing or not confusing? Perpendicular or not perpendicular? Best fit, I'm sure all of you have seen, right? In one way or the other. Sum of errors. Okay. So sum of errors. What is that error? So this is my x. Okay. So this was my original point. What is the new point? This is my new point, right? So this is, let's say, yi dash. So let me call it, let's call this y. Let me call this y dash. The x also changes in this case, right? So this will be some x dash y dash. This is x comma z, and this is your x comma y. Okay, now tell me what in least square fit, what do you do? You have all done this. I can, at one point in time in life somewhere you would have done linear regression, even if you are in second year. Y minus z. Okay. Any other suggestions? Okay, so this is your OLS, ordinary least square. We'll see this in the next class. Okay. Is this the right approach to? So okay, fine. Okay, who was it? Shivam? No, Nakul. Yes. Finish the argument. You started it, right? Okay, summation of y dash. So you're saying that this is this. Okay. So I will write this as my vector x, and this I will write as x dash. So this is a two-dimensional vector. Is that what you're saying? And what you are saying in terms of what we do in OLS is, that's fair. Okay, which one is the better strategy? So fine. Okay, let's Nakul. So we follow Nakul's approach for now. Let's say, right. So I take then I should take this point as my one. Okay. So fine. I figured out uh, my point, and I can do the same observation. I can do the same thing, and I figure out what my line is. Okay, fair enough. So you can. This is what your 1D data looks like. I want you to give me back the 2D points. Can you give it back to me with this? Mm-hmm. Mm-hmm. So yeah, so you're like 2 3 steps ahead. But before we go there, like what is the intuition? Like how do you figure out this? Okay, so now okay, now that's one more step you're taken, one more step ahead. Slow down. What exactly is the goal, right? Mm-hmm. Least variation between the groups. Maximizing the variation. Okay, Mayurakshi has seen it. You have seen it? Sorry? Okay, okay, good. Yeah, my first question, actually, I think I'm not doing a good job because I did not explain what the difference is, right? So there are two sort of regimes that came up, right? One regime is to minimize this this error, right? Sharda, is that you said perpendicular? Okay, fine. But so who said this? Which one was it? Okay, somebody said that we have to sort of figure out that this is the error in which you have to minimize it. And then the other regime is this, and it gives you, both of them give you some fit, right? And both of them give you this. I want to now use this data to reconstruct my original data. Okay, how will I do that? Can I do that at all actually? Hmm. Cos theta with respect to what? Okay, best fit line. Okay, this is, let's assume this is BF. This is best fit. Projecting the line on the, okay, this one. Okay, okay. So we will not finish this, but let me show you an animation and let's try to see whether that helps. Okay. It took me a while to get that animation right. I hope it runs. So I would like to go from simplest problem, right? I would want to go from 2D to 1D. Obviously, there are multiple ways to do it. Okay, there are, so some ideas were about being able to use best fit line. Some ideas were being able to use some sort of a calculation which minimizes this distance, and then somehow that is this line, this whatever is the corresponding value of x here, that becomes your line. So this will be one way to do it. The second way was that we project this, right? So this projection, so I'll write the projection one version as x, and that is a good reconstruction, right? Or this is a good dimension. I think both the answers are valid, but I'm going to condition this on the fact that I want to be able to reconstruct my original data from this, and I know I'll not be able to do this 100% right, but when I do this, I want to retain the originality of the original points as much as I can. Okay, so I have, when you again go from this to 2D, I want my what's called my reconstruction error. Okay, so we'll formalize this in the next class, but I want to show you animation and see whether that is helpful. Okay, so just notice what is happening here, and oh sorry, and tell me what do you see. What is happening? So this is 2D. This line that you're seeing, I've taken all 180-degree versions of this line. Okay, they can be anywhere in that one. So this is rotating all 180 degrees or whatever 360 degrees. And what you're seeing is these red points are what you would have calculated depending on how you define your projection. Where should this line, which version of the line should I choose? Green and red. Okay, and what is green and what is red? Okay, major axis, minor axis. But like what is so special about those two? Okay, so getting warmer, but I asked you for reconstruction error and not variance. Hmm. 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 Okay, so we'll finish the argument in the next class. But is this clear? Like what is happening here? So you'll see that if you focus on those red points, right? Those red are the projections. You see something special happens the moment it comes here. What is that special thing that's happening? Whether either it comes here or it comes here. If it comes where, here or this side? Okay. And what about now? And what about here? So I'll try to make a higher resolution version of this, and that will hopefully help you sort of figure out what is going on. So I'll not tell you what exactly is going on, but I'll put the code for you to be able to run this. You can run this simulation, and you should be able to see what tries to happen there, right? And we'll formalize this in the next class. And please submit your assignments by Monday, 11:59. If you have any questions, please let me know. Um, my office hours are not today, but if you want to meet, you can meet on. You can just send me a message, and I'm happy to meet. Okay? Thank you.